In this video, I am going to show you how I dual booted my STM32 microcontroller. Here I have two firmwares that does simple task of blinking LEDs and throw some data on the UART. I have built these firmwares on Atollic TrueSTUDIO. I am going to place both these firmwares in the flash memory of STM32 and then run any of these as per as my need. Before we go ahead and see how it is done, let me tell you how it works. All the user program of the microcontroller is located in the flash memory, and this particular microcontroller that I am using, that is STM32F411, has 512 KBs of flash divided unequally into 8 sectors. I am going to place my firmware 1 starting at sector 3 and firmware 2 starting at sector 6. But by default, when the microcontroller is configured to boot from flash memory, the controller boots from the address 0808000000, which falls in sector 0. So here at sector 0, I need to write a code that will ask me which firmware I want to be running at that particular instance, and the microcontroller should boot from that particular sector. Such piece of code is called as bootloader. So dual booting a microcontroller is all about making a bootloader. Before I show you how to make a bootloader for STM32, let's see what these firmwares 1 and 2 does. So here you see firmware 1. So on flashing this onto the controller, you can see something printing on the UART. So it says welcome to application 1, and then it keeps blinking red and orange LEDs, and then it keeps printing you're in application 1. So now let me flash the firmware 2 here. It's similar to the firmware 1, but it on the start it says welcome to application 2, and then it keeps printing you're in application 2, and then it also blinks blue and green LEDs. Yeah, so here you can see it blinks blue and green LEDs. So now let me go and start building bootloader. Let me show you how I'm doing. So here I'm using STM32 CUBEMX software to generate the initialization code. I think this is very handy for every project. So searching my discovery board, STM32F411, looks messy, clearing all pinouts. So I'll be using 4 LEDs here that are on board, that is red, orange, green and blue. So I'll also be requiring one UART here, so that I can take input from the user. Using UART2, and then enabling interrupt here. So actually there is some problem with this particular board here. There's a lot of noise on the UART lines. So I will have to pull up the UART lines here. So I'm using internal pull up. So enabling internal pull up here on the software. So, and the major hardware change I've made here is, in this particular bootloader firmware, I'm actually using external crystal, that is high speed external crystal, 8 MHz crystal, that is on the board. But for both firmware 1 and firmware 2 I showed earlier, I haven't used any external crystal. I was using internal high speed internal oscillator itself. So the code is generated, and now let me enable the interrupts here with this particular function. So I'm using receive interrupt. So this is the receive interrupt enable. 8-bit data array, just to receive the data into that array. So this is the function I would be requiring to call to enable the interrupt and receive data as well. But this also requires an callback function. Okay, receive complete callback function. That, yeah, this is the receive complete callback function. So I'll be calling this in my main function. I'll be uh, declaring it in my main file. So here it goes. So first I'll be checking whether the interrupt is received from UART2 or not. Okay. So if this particular interrupt is from UART2, then I'll be checking what the data is. So here I'm only going to check whether the data is either 1 or 2. So let's keep it simple for now. So if the first byte of the received data is 1, then I'll say jump to firmware 1. If the first byte of received data is 2, then let me jump to firmware 2. Alright, now declaring this jump to variable here. Okay, and initializing it to 0. Alright. So now let me poll for this variable in my while loop. So before that, these are some debug scripts that I always use. So I'll just copy my debug scripts so that I need not write every time. Okay, yeah. So now I'll be polling for the jump to variable here. In case 1, when jump2 is 1, I'm just printing jumping to, let's say, application 1 or firmware 1. Then breaking this thing, and then in case 2, where I'll be printing jumping to firmware 2. This is not the best debug script here. So while in default case I'll be toggling the LEDs here at 1000 millisecond frequency. Okay, in the start, let me also say welcome to Beyond Breadboards bootloader. Looks great. And then ask user which firmware he wants to jump to. Choose the firmware to jump to. 1/2 question mark. Alright, looks great. Okay, let's build it till here and check whether the interrupt is working fine. Okay, alright. Now it's time. Let me write the functions to jump to user code. So here I'm making new files, that is bootloader.h and .c. So in these files I'm going to implement my jump to user application code. First jump to firmware 1 code, and then also declare the macros to your firmware base addresses, that is base address of sector 3 and sector 6. So before we continue, let me first show you how the data in the STM flash is organized. The first word from the base address of the firmware is the address in the RAM, and on the boot the main stack pointer is set to this address. The second word from the base address of the firmware is the address of the reset handler of this particular firmware. So now let me assign the reset handler address to a function pointer here. Okay. Yeah. So the second, as I said to you guys, that second word is the address of the reset handler of that particular user application. So before we jump to user firmware, so it is important for us to actually disable some important system calls. So let me do rcc dinit. So rcc dinit actually resets the whole system clock, and then it runs everything on the internal crystal, and then halt deinitialize actually resets all the peripherals after switching to the internal clock. Now, since we don't want any interrupts from SysTick as well, let's load everything to 0. So we don't want any SysTick time interrupts or any interrupts that is going to disturb our code, as this is the crucial part, since this is the part where we are handling the whole control to different application. So here let me get the MSP value here. So the first word in the base address of any particular firmware is going to be taken by the MSP. Oh, before that, what we actually required to do is there's a VTOR register in after ARM Cortex M3 family. So this is M4. So here also there is VTOR register that should be set to the base address. So later the MSP should be set. And now let's call the app reset handler. Alright, let's copy the same code for jump to firmware 2 and let's change all these addresses. We also need to actually place our firmware 1 and firmware 2 in their respective positions there. So what we'll first do is we'll place these firmwares before we run our bootloader, flash our bootloader code there. So in that particular firmware, you have a linker file, and change the origin of that in that linker file to your respective start address or the place where you want to, or the location where you want to place it. So here my firmware 1 lies in sector 3, so I am putting it in, changing the origin to 0x0800C000. And another change that we have to do is we have to change the VT over offset even in the application code as well. So that you can do it in this system underscore STM32F411E or file. So remember the flash base address. On ORing the flash base address, the vector table offset, you have to get your firmware start address or that particular sector start address. So my firmware vector table offset would be C000 in my previous code. For firmware 1 it would be C000, and for firmware 2 it would be 40000. So now let me go and place both the firmwares and see whether it is placed in the respective location or not. So before showing, let me erase the complete chip and flash it again with debug itself. So you can see the whole memory is empty right now. There's nothing at either of these addresses. Nothing here as well. Okay, now let me go and flash firmware 1 after our settings are done, alright, and check for the start address. So it is 0x0800C0000. Yeah, this is the firmware one start address. Oops, it seems wrong. Okay, now okay, the start address is actually 0x0800C000. Yeah, so here you can see there's a code, there's a firmware here that is flashed from this particular address, and the first word of the start address is actually the address that stack pointer will take in, and the second word is a reset hand. This particular word is a reset handler, address of the reset handler of this particular firmware. So handling to main function lies in the reset handler part. So now going to flash firmware 2 there in its respective address, that is sector 6. Okay, all right. So now let me go and add the implemented gem2 firmware 1 and firmware 2 functions in my main.c there. So before that, I need to include my bootloader.h here, and then call gem2 firmware 1 in case 1, and gem2 firmware 2 in case 2. Yeah, it's almost done. And compiled without errors. So I also added a small UART animation kind of thing so that it can become more interesting there. Yeah, it works fine. So here when I press reset, it says it's asking me which firmware I want to go, and when I press 1, it jumps to application 1. You can see it says welcome to application 1, and the red and orange LED is blinking, and when I press 2, it says welcome to application 2, and you can see blue and green LEDs blinking there.